Hey there, my name is Alejandro, and welcome back for day 172 of me doing the Daily LeetCode challenge until I reach 1 year's worth of Greek contributions here on GitHub. So today is problems for January 4th, 2024, and let's get straight into it. Okay, today we get a LeetCode medium from 1930, unique length 3 palindromic subsequences. Given, subsequences, not substrings, interesting. I'm already thinking DP here. Okay, given a string S, return the number of unique palindromes of length 3 that are subsequences of S. Notice that if there are multiple ways to obtain the same subsequence, it is still only counted once. Okay. A palindrome is a string that reads the same forwards and backwards. A subsequence of a string is a new string generated from the original string with some characters can be non-deleted from sure. For example, ACE is a subsequence of makes sense. Okay. So palindromic subsequences of length 3, and if a subsequence can be made multiple times, it's counted only once. Now that's interesting, right? Because obviously it would be a lot easier if it was the same sequence. So basically we need to keep track of a set of solutions, which is fine because each of them is of length 3, so you know it's like constant space per palindrome. Like for example, it's like, you know, checking if something is in there is like, you know, it's always constant time, just because it's like you're always comparing with strings of length 3, and where 3 is a fixed number, so it's like, you know, we can kind of abuse the fact that that's going to make some things of 1. What are the constraints for this problem? Okay, as that length is up to 10 to the 5, so we need a linear time solution or an n log n solution in the very best case. Okay, which means that okay, well, my first idea was going to be some dp 2d thing, which obviously we cannot do. But this makes sense, right? Because, okay, it's going to be length 3. So, okay, so it's palindromes that are specifically length 3. So it just means that it needs to be the first letter and the last letter are the same, and then the middle letter, doesn't matter what it is, but there needs to be a letter in there. Okay, so, okay. So if I have a letter, basically, if I have a letter like, okay, here's just showing us a subsequence, not a palindromic subsequence. Right, so for example, if we have a letter like A, we want to look at other possible characters of A, but, okay, so we need to look at other possible characters of A, and then for each character in between, that makes a valid subsequence. Now the only problem is that that's going to be like, you know, n squared time here, right? How do you do this in non-n squared time? So if I have a character A here, right, and I like look at the character A here, it's like, okay, you have AAA, you have ABA, you have ACA. I guess maybe that's where the where this part comes into play, where if you've done something once, you don't have to do it again. So once we're done with the A's, we're done with them forever, right? And is this, yeah, this is only lowercase English letters. So really you can do like, you know, all the subsequences that start and end with A. This is really abusing the fact that there's a constant amount of English letters, right? Because something you could do, this is even weird, right? But you could do like, you know, count essentially the frequency of each letter for like, you know, every single, and basically do like prefix sums to like essentially get the count of like letters up to an index I. So you could essentially get the frequency of each letter of the alphabet between any subset I to J, and then it's like, you know, for all the A's, like for example, if you have an A, you essentially want, for every single letter of the alphabet, you want its leftmost index and its rightmost index, right? And then once you have those, it's like, okay, between those two leftmost and rightmost things, it's like, how many characters do I have sandwiched in between those two indices, right? So essentially the leftmost index +1 and the rightmost index -1. Maybe there's no letters, right? So my idea is essentially to abuse the fact that you have a constant amount of lowercase English letters, right? You start getting to the point where it's like, you know, 3 times 26 times 10 to the 5 is like, yeah, starts getting into the stretchy area of things, but I think it's possible, right? 10 to the 6 is usually okay on LeetCode. So it becomes like, you know, 6 times 10 to the 6 it starts getting a little wishy-washy, but I think it's okay. Should be okay. Right, one thing we can do is, first of all, alphabet is equal to A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And then here, yeah, this is going to be interesting. Edge indices is equal to border indices is equal to a dictionary. We're going to do letter for letter in alphabet. That's going to point to a two-element list element. First, it's going to be float of infinity, float of negative infinity, right? We'll do for letter in S, we'll do if border indices of letter leftmost comma rightmost is going to be equal 0, 1, leftmost index, this is none. Here we'll say this guy becomes, here we'll do I comma letter in enumerate S becomes index I. Otherwise, we'll say of rightmost, we always want this to be the maximum one, right? So we're going to keep updating it with I. Okay, now here I want to print f string border indices equals, and then what do we return in this thing? We return a number. So for now, let's just return -1. Border indices, so A is 0, 4. Does this make sense? So yeah, leftmost index of A is 0. 0, 1, 2, 3, 4 is the rightmost index. For B, there's only one index, and it's here. So first of all, for something like B, we know that there's only one instance of it. So we know that there is no possibilities of a palindrome, right? And then for each one, we have to be careful about the indices that are between there, right? So here what we need to do is something like prefix. Again, yeah, we're really abusing the fact that there's a constant amount of English letters here, right? We're really abusing this fact. But hey, you know what? Let's use this to our advantage, because even for doing prefix differences, you're gonna have to, like, you know, loop over every single letter of the alphabet. It's again and again and again. It's just like, you know, we're abusing the fact that, hey, 26 letters is constant time, but yeah, it doesn't feel comfortable for sure, right? Because if it's like, you know, up to M unique characters, then it's like you start getting into spicy trouble, right? And so there's probably a better way to do this, but yeah, for now let's just go through this, because it's kind of what I have on my mind. So here we're gonna do prefix frequencies. What should we do? I guess we can do do we add a copy every time? I guess we add a it's just weird, right? But it's like it's like I'm doing this times 20. I mean, I'm gonna do that times 26 work anyways, right? So whether I do that again, like it's yeah, I'm really pushing, you know, big O to its limit here. But okay, let's just do that. We'll do a dictionary. We'll even do a default dict of int. No, here we'll make this an array, right? It's just that we'll keep pushing stuff in there. Frequency dict is equal to a default dict of int. For letter in S, here what we're gonna say is prefix frequency dict of letter plus or equal to 1. We just saw it one more time, and here prefix frequency dot append a copy of the frequency dict, of which there are at least 26 keys, because those are the letters of the English alphabet. So this is technically of one work, since at most 26 keys. Yeah, it doesn't make me feel very comfortable, but that's technically a technicality, right? Okay. So now, here you can also do printf string prefix frequencies. Yeah, so at the beginning we have 1A, then we have 2A's, then we have 2A's and a B, 2A's and a B and a C, 3A's and a B and a C, right? So it's like, now what I want to be able to do is essentially from two indices, essentially get their subtraction, right? Okay, so now let's do get subarray frequencies, self and an I and a J. Here we'll do self.s equals s. Here we'll say, we don't even need this. Here we'll do self.prefix frec. So we have 0 to I, 0 to, yeah, so essentially it's like what we want to do. di, dj equals self.prefix frec of I, self.prefix frec of j. A dictionary of j key points to j val. Or here we'll do key, comma, so for key and DJ. And here we'll say di of key, dj of key, minus, also it might help it to not do things as default dicts later on, right? To do, consider not using default dict. So that essentially, yeah, even though like the big O is like in terms of 26, we like, let's say that key didn't exist inside of di, it's annoying to essentially make it exist so that then it's like used again later on and so on. Like, we might as well prevent that for efficiency reasons, right? But here we return a new dictionary. Oh yeah, dj of key minus di of key. This has to be a positive number because you go greater with dj. So yeah, this is from an I and a j, right? And now here I'll say for letter in alphabet. Is none. At least two of the same letter to form any palindromes of length 3 with it. So continue in that case. Otherwise we have stuff. We have stuff to go with. So assert of leftmost is not none. Now we'll do self that gets subarray frequencies from okay, we'll do that. count is equal to sum of val greater than 0 for val in d dot values. Right, there's at least one of that letter, even if it's the same letter as the palindrome 1. Because again, we're going through every single letter in the alphabet. So basically what I'm doing is like, okay, we want like 3 palindromes, right? So it means that the first letter must be the last letter, right? And since there's only English letters, it's like we'll do the case where it's like, you know, A, and then a letter in the middle, and then B, and then a letter in the middle, and like C, and a letter in the middle, right? So it's like here, it's like, you know, how many possible letters can go in the middle, you know, between essentially, because you're only counting the same subsequence once, right? It's like you're only going to count like, you know, you only, like for any letter like A, for example, really what you want to care about is like, you know, the greatest span of the letters that you can put inside of the palindromes that start and end with A, right? Which you'll essentially get by looking at the leftmost index of an A inside of S and the rightmost index of an S of A inside of S. Essentially all the letters that you have in between there is like essentially the letters that you can put between two A's. And that's essentially kind of the limit of the number of palindromes you can have, right? And every single, you know, letter is gonna kind of have, you know, I guess this might not be the most inefficient thing in the world. Actually, yeah, this might not even be the most inefficient thing in the world, right? Because here I'm looping over alphabet, not even the string S, right? So I'm actually kind of over exaggerating. This might actually not even be that inefficient at all. So here we just need a res. Right? Okay. Yeah, I'm not missing an alphabet letter. Oh, is this going to be I minus 1 maybe? Yeah, because I want I to j, right? If I greater than 0, it's default dict of int, maybe? Right, okay, if I remove this, essentially, do I get a wrong submission, right? That's what I want to ask myself. Okay, first of all, output limit exceeded. Okay, prints can become hashtag prints. So I want to use this test case first of all. Okay, so that one is accepted. Okay, it works. Completion streak 172 days. Consistency is key. See ya tomorrow. Okay. And we're not even that bad. We're at 52%. Okay, so there seems to be like 2 standard deviation curves. We're near to this one. Okay. Okay, that's not that bad. Okay, so we don't even need the... Okay. No worries. No, I guess it's because... I don't know. It feels like this would have been necessary, right? So what if I is equal to 0? Which will be necessarily the case for one of them, right? It's just that if it's 0... yeah, feels kind of sus. Maybe they don't have strong enough test cases. This feels more correct. I don't know. This feels like they just don't have enough strong test cases. You know what I mean? Yeah. Okay. Here, what I'd rather do is something like this, and then here I'd rather do di dot get key comma 0 and stop using default dict. Right? Not in frec dict. One else, right, for now. Yeah, so okay, that's already making our runtime a lot faster. Okay. Or we can even do a frec dict of letter. Frec dict.get letter comma 0 plus 1, right? Maybe that makes us even faster. Here, yeah, it's a bit annoying to have to make a copy every single time. Yeah, seems like we're right on the same track with that. Here we can do let's do get so count. Return sum of now count is equal to self dot r. Okay, and now does this make me go faster? Okay, just barely. Okay. Maybe count. Barely. This also seemed to work just fine without that. We can also do and then count right. Okay, we're still at the same pace here. Maybe we do for key and DJ. Plus or equal to DJ of key greater than di dot get key comma 0. Yeah, I'm just stuck here. Okay. I think I'm kind of stuck there. I can also remove this assert. I can also remove this, remove some inefficient stuff here and there. Yeah, okay, so no matter what, yeah, it seems like we're going to need to get to the 182 range for us to beat the 73.19%. So it's like, okay, it seems like, you know, this is kind of like the furthest that we'll get with our current implementation. Okay, so we have a 73% beating solution. So I like to, you know, sometimes kind of like kind of push my O of 1 inefficiencies here and there to see, like, you know, how far can I kind of get. But yeah, here it doesn't seem if L greater than 0, else that's why. L is always greater than 0 because I put a +1 here. L always greater than 0. Always. There we go. That's why. Okay. So that, yeah. So it's not that they don't have sufficient test cases. It's that, like, yeah, I would need that code, but since we do +1 on L, even if this was 0, by doing +1, yeah, that makes sense. Makes a lot of sense. Here we can get rid of these functions. There we go. There we go. If anything, maybe we could make things faster if we use an array of length 26 every time. Yeah, maybe we should use an array of length 26 every time, right? Let's do frequency array instead is equal to 0 times 26. I don't know. Maybe, I don't know if it'd be faster or slower. Faster because it's an array, but slower because it's like, you know, technically I didn't need all 26 keys to be populated at any single point in time. Here we'll say ord of a is equal to ord of little a at the very beginning. We'll do frequency array. Right here, let's do f string prefix frequencies, and here we'll do return 0 for now. Yeah, so at the beginning we have 1a, then yeah, like here it's like we have 3 a's, 1b, 1c. Yeah, okay, this is fine. This is completely fine. It's just, yeah, it feels like it would be slower, but maybe in the higher test cases it turns out to be a bit faster. We'll see. Otherwise, we'll keep the dictionary solution. AI array j is equal to prefix frec minus 1 prefix frec of r. Actually, no, this is plus 1 minus 1, so it could be 0. Okay, I'm actually kind of tripping. Oh, but yeah, it doesn't matter. It's L itself. Yeah. L minus 1 will always be greater or equal to 0. So yeah, it's fine. It's fine. I'm always stressing for no reason. And AJ AI of index greater than 0, which means that you really want this to be greater than that, for index in range 26. Okay, something like this. Okay, so that's working. Print. Okay, so is this faster? It's slower, much slower. Interesting. Interessante, ladies and gentlemen. Okay, it still puts us in kind of this standard deviation curve. But yeah, it makes sense. With the dictionary, yeah, the thing is with the dictionary, at the very least, we didn't have to populate all 26 elements if we absolutely didn't have to. Versus here, it's like, you know, when you use an array of length 26, you always are no matter what. So you don't technically get that advantage, even though looking up something in an array is probably faster than looking up something inside of a hash map. So, I mean, here we can also do, you know, test something else like for minus plus or equal to AJ of IDX. Maybe this is faster, but I doubt it. You know, it's not going to save us hundreds of milliseconds. So yeah, it's just not. So we can get rid of this. There you go. We can put this back to how it was. Can get rid of this. Can put this to back how it was. Can get rid of this. Get this back to how it was. And there we go. Nice. If anything, we can probably put these guys up here. And just put it in the same for loop as this one's, right? That way we have everything inside of one for loop, so maybe this is a little bit faster. Right? You know, small tiny optimizations here and there. Yeah, it doesn't really matter at all, right? At the end of the day, it's all the same work. Blah, 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 blah. Yeah. I mean, okay, we're not going to make it much more efficient, so yeah, we'll just submit one last time, one final time. But yeah, we're not getting past around the, 312, 311 MS mark and so on. We're right here at the beginning of the standard deviation curve. Doesn't matter how many times we resubmit, it doesn't seem like we're faster than these guys, but that's not a worry in the world. It seems like, it's the O of 1 stuff anyway, right? This is technically a little bit inefficient to do a length through array and so on. Maybe there's a better way of doing things, even if it's literally like bit masking, right? And it's like yeah, some way of knowing stuff. But honestly, I like my solution. I'll explain how I did my solution, and we'll just leave it at that. So I'll drink some water, and then we'll get straight into it. Okay, there we go. So, as always, in all my videos, I do a quick recap if I was able to solve the problem. So for this one, essentially, what they wanted you to find is essentially find the unique length-3 palindromic subsequences. So what this meant is you're given a string S, and you want to find all subsequences of length 3 that happen to be palindromic substrings, right? And you only want to know the count of unique palindromes of length 3, not the total number of palindromes of length 3, right? And it's the very first thing that I realized is like, okay, when you're talking about palindromes of length 3, first of all, it's like, it's fixed, right? It must be that you essentially have, you have 3 letters, right? We'll call them like, X, Y, and Z, and we don't know what these letters represent, right? It could be like, X is equal to A, whatever. What you need is essentially for this guy to be equal to this guy, right? You don't care about Y itself, but essentially the pattern you need to follow is something like X, Y, X, right? So Y could definitely be X, right? So it's like, if you have X, 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 right, the same letter over and over and over, it's essentially going to be a palindrome, right? A, for example, is a palindrome inside of itself, right? And just the middle character, it could be totally anything, right? It's like if you have something like ABA, that's a palindrome. If you have something like BCB, then that's a palindrome, right? As long as the first and the last letter are the same, you essentially have a length 3 palindrome, right? You just need any character in the middle, but you need the first and last characters, the first and third character, to essentially be the same thing, right? Now, one thing that's nice about this problem is that they essentially constrained S to only be consisting of lowercase English letters, of which there's 26 many, which, if you realize, is a constant amount of letters, right? So that's kind of a power thing to leverage, because one thing we can do is like, okay, I think there was a big hint in them saying that they want unique, because if we really think about it, palindromes of length 3 only exist when the first letter equals the last. And we're only dealt with English lowercase letters, right? Which means that, like, essentially for the very first letter, there's only 26 possible permutations, right? It's going to be A or B or C or D or E or all the way up to Z, right? Now, we know that if we fix, like, let's say the first letter to be an A, then that means that the last letter must be an A. Right? And we only want the unique subsequences, such as like, if you find ABA once and then you find ABA somewhere else again, you only want to count that once, right? You don't want to count the total number of length 3 palindromic substrings. You want to count the total number of unique length 3 palindromic subsequences, right? Not substrings, sorry. Which actually makes things very interesting, right? Because at this point then, you just have to focus on, well, I need like, something that starts with an A, something that ends with an A, and essentially any single possible character that I can sandwich in between them, right? So for example, like, this A and this A, how many characters can you sandwich in between them? Well, then nothing, right? Because there's no characters between them, right? But that's not very interesting, right? If anything, and what I did inside of my solution is like, what I'd like to do is grab my leftmost index of an A and my rightmost index of an A, right? Because if I can only count things once, right? I can only count things once. If I grab the left and rightmost index of A, where I'm focusing on palindromes that of length 3 that start and end with A here, bear with me, but it's the same thing for the 25 other letters of the English alphabet. then there's no reason for me not to grab the leftmost index and the rightmost index and essentially look at every single character sandwiched in between there, right? Because if I pick anything else, right, if I pick this A and this A, well, I'm essentially leaving characters that were in here on the table. In this case, it doesn't really affect anything, but like, you know, with a much larger string, it might have. Or like, you know, at worst case, it's like, you know, if I pick these two A's, well, obviously I'm leaving a lot of letters on the table, right? Here it's like, oh, between this A and this A, there's nothing between them. So it's like, oh, there's no palindromes of length 3 that start and end with A. That's totally wrong, right? Well, for example, you know, here we say like ABA is one, AAA is one, ACA is one. So obviously there's way more than just 0 palindromic substrings that start and end with A, right? And so my idea is to essentially grab the left and rightmost indexes of the letter A. And the reason why we're going to do this is because if we grab the left and rightmost index, right, essentially every single character that's sandwiched between those two indices, right, not including the indices themselves, because obviously they're needed to be as the left and right parts of the length 3 palindrome. Since we're dealing with subsequences here, every single letter sandwiched between those two is fair game to be the central letter of our palindrome, right? Remember, we need this XYX form. Well, if we fix it to be the A's, we essentially say, hey, X must be an A, X must be an A. So we want the leftmost and rightmost index of an A, because that way every single other letter in between those two indices, the leftmost and rightmost index of A, are fair game to essentially be our Y, right? And they will encapsulate every single unique possible palindromic length 3 unique substring that we could possibly have that starts and ends with A, because we're grabbing the leftmost and rightmost indices and looking at all the letters in between them. If we grab any two indices, we're potentially leaving some unique substrings on the table that we could have otherwise used to include in our solution. So that's why we grab the left and rightmost substrings, because that essentially guarantee us that we'll go through every single unique palindromic substring if they all exist, right? So this is actually what I did. So in this case, we grabbed, you know, this index and this index, so like 0 and 4, right? And then we essentially would look at every single letter in between, and essentially we want to count the number of letters uniquely that happen between these two A's, right? In this case, we have A, B, and C, right? So there will be a length 3 palindrome that starts and ends with A, with B in the middle, and another one with A in the middle, and another one with C in the middle, right? Because we have B, A, and C in between these two A's, that are leftmost and rightmost A's. That's exactly what you see. One with AAA, one with ABA, and one with ACA. If we take another example here, like for example, here we do the left and rightmost index of B. Well, between those, there's all these letters here, right? Here we have a B, a C, a B, and an A, right? In reality, we only have uniquely an A and a B and a C, right? We're not going to count BBB more than once, right? Because we only care about the unique total substrings. So here we'll say, okay, I claim that with B, I'll have, you know, a palindromic substring that starts and ends with B, and in the middle there will be one with a B, one with a C, and one with an A, right? And let's look over here. Yep, there's BBB, there's BCB, and there's BAB, exactly as we expected, right? If we look at the left and rightmost indexes of A, it's here and here. The only letter sandwich between them is here, so the only palindromic substring that starts and ends with A will be ABA, which is exactly what we see over here, right? So the point is that for every single letter of the alphabet, A, B, C, D, E, F, G, all the way up to Z, we'll essentially consider the case where it's like, okay, what if that is the first and third letter of that palindromic substring? I want to know, you know, how many palindromic substrings I have between those two. So the idea is essentially grab the leftmost index of, say, Z, the rightmost index of, say, you know, Z, and essentially look between those two indices and look at every single letter that happens at least once between those two indices, right? And that's essentially going to be the number of unique palindromes that start and end with Z, right? And we'll do that for all 26 letters to essentially get all unique palindromic length 3 subsequences inside of that. Sorry, this is a huge mouthful, and I kept seeing substrings, but it's subsequences, and obviously that's a very important part of the problem. Otherwise, we wouldn't be able to do it, because that's why we're allowed to consider any single letter in between, right? And so in terms of how I did this in the code, the very first thing that I want is essentially, okay, for every single letter in the alphabet, I want its left and rightmost index, right? So here I have every single letter in the alphabet. Here, ignore what this does, but essentially I'm going to loop over every single element in S, and what I'm going to say is like, okay, this is every single letter in S. This just happens to be index of that letter, right? So for every index, like this is the same thing as doing for I in range length S, and then letter is equal to S of I, right? It's the very same thing. Here we'll say, you know, border of indices of letter. So essentially border of indices is a dictionary, which the keys are going to be all 26 letters of the alphabet, and their values are essentially going to be a two-element tuple, the first being the leftmost index, and the second being the rightmost index, right? Here, that's why I have leftmost and rightmost as 0 and 1, because, you know, this is an array, so index 0 will be the leftmost index, and index 1 will be the rightmost index, right here. And so here, that way, it's like, you know, if I do border indices of letter for every single letter in S, and I do, okay, if the leftmost index is none, that means that I haven't found a leftmost index for it yet, so I put that the leftmost index as my current I, because that's the very first time that I see this letter inside border indices, right? Otherwise, if Warren indices letter of leftmost is not none, that means I've already computed the leftmost index, right? The very first index that I see of any letter will be its leftmost index, right? Otherwise, every single index that I see for a letter onwards, right? I.e., if this is not none because I've already seen a letter before, then I'm going to be like, okay, the current index I is the rightmost index I've seen so far for this letter, so I'll update it to that value, right? Here you could do max if you want, but the point is that every single time we revisit this letter, this will be the rightmost index that we found for that letter. So we'll keep updating, letter of rightmost every single time we revisit the letter with a higher index over and over and over, right? Because here we go from low indices to large indices, right? So that's kind of the point, and that way it's like once we're done with this for loop, essentially we'll just have for every single letter a 2-element tuple where the first or a 2-element array where the first element is essentially the leftmost index of that letter, and the second element is the rightmost index of that letter, right? And there must be at least 2 indices, right? The very first time that I add a letter, I'll only add its leftmost index, I won't add its rightmost index, right? And that way, later on in the problem, when I go through every single letter in the alphabet, because I want to go through every single palindrome that starts and ends with that letter and has stuff in between, I'll check if, leftmost, if the rightmost index is none, right? Then I know that both, that there's only at most one occurrence of that letter. Since there's at most one occurrence of the letter, I cannot form palindromes with that start and end with that letter, right? Because I need at least 2, right? For example, for ABA, I need at least one leftmost index of A and one rightmost index of A that were different, because otherwise I essentially do not have any possible palindromes that start and end with that letter, right? If I wanted to start and end with that letter, I need at least 2 of that letter inside of my string S, and if I only have 1, then I cannot form any palindromes, right? And the way that I'll check that is by looking at, hey, have I set the rightmost index one, right? Because at first I'll set the leftmost one the very first time that I see a letter, and then the second and any other time that I see it again, I'll essentially keep updating the rightmost value, right? So at any point in time when I loop through the letters, I see that if the rightmost value is still none, then that means that I've only had at most 1 occurrence of that letter happen in string S, so I know that I don't have to deal with this, right? So that's just a tiny little optimization there, and yeah, but that's essentially how I get the left and rightmost indices of every single letter inside of S, right? And then also another thing that I do is a frequency dict. So what does this mean? Essentially, here what I'm going to do is some prefix sums, because essentially what I want is when I have the leftmost and rightmost index of a certain letter, like A, right? I essentially want to know, okay, how many letters are essentially sandwiched in between there, but in the worst case, that would be O of n time, right? And if I do this, for every single letter in the alphabet, that's kind of inefficient, right? I guess technically you can get away with it because there's a constant amount of English lowercase letters, and it'll be that's why I was saying that this is not going to be as inefficient as I thought. But technically, I think this might pass under the constraints here. Because 1096 times 10 to the 5, you start, you're like 2.6 times 10 to the 6. You should be able to pass it on LeetCode, but otherwise, essentially, for every single letter in the alphabet, what you'd be doing is O of n work, right? And if you can avoid that, you should, right? And so that's essentially exactly what I did. So where it's like, okay, between the leftmost and rightmost index, I essentially want to count the number of unique elements, right? And one way that you could do that essentially is like, okay, for every single, what I could do is essentially, what I could do is this, right? S is equal to a set, and here I can just do for letter in range L and R inclusive, or for index here we'll do s.add, s of I, or here we'll do count set, right? Just because s is already the string name, and then rest plus or equal to length of count set, right? And so something like this might work. Let me just see. Why wouldn't it work? Why wouldn't it work? S of I, right? I'm doing this, right? Oh, S of index. I is defined somewhere else somehow. Yeah, so this works, but I don't know if, does this time limit exceed it or does this get accepted? Okay, so this gets accepted. Somehow it's not too terribly slow compared to my solution, but yeah, it's almost like, 3 times slower. So yeah, technically something like this would get accepted, which is kind of the naive way of doing things. It's just that I immediately framed away from doing that in my mind, which, okay, is good. But yeah, technically you could do it this way. So essentially what I'm doing here is like, okay, once you have the leftmost and rightmost index of a letter, right? then essentially what you can do is like, okay, I essentially want to know how many unique letters are between those two indices, right? So for example, if I have the leftmost and rightmost index of A, right? For example, or like, a better example was like with these B's, right? This is the rightmost index of B, leftmost index of B. It's essentially like how many letters uniquely happen in here, right? Here there's 4 total letters, right? But B is duplicated. So I only care about, B existing once, C existing once, and A existing once, right? So essentially between your leftmost and rightmost index of any particular letter in the alphabet, in this case it just happens to be B here, right? You want to count the number of unique letters that exist between those two B's, because essentially each of those unique letters will essentially create a new unique palindromic subsequence of length 3 inside of the string S, right? And so one way you could do that is essentially what I just showcased right there. Go from like, that left index and right index, and essentially, build up a set, and for every single letter in between there, add it into the set, and that way it's like at the very end you can just return the length of the set, because that'll be the number of unique characters. The only problem with that is that it's O of n time, right? And so it's like every single query you'll have to do O of n work. A much better way of doing things is essentially just investing O of n work up front to essentially do a prefix sums count blah 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 kind of thing, where it's like essentially here I wish I could do this a bit more efficiently without having to do copy every single time, even though this is O of 1 work technically. But okay, we'll just get around that. But essentially what I did here is like, okay, for every single index I'm going to have access to the frequency of each letter, right? So essentially, frequency of dict, right? Or prefix frequencies, what I should say, right? This is just the dictionary that I'm building, and then I'm copying every single time. Here, prefix frequency of I equals frequency count of each letter in S from 0 up to I inclusive, right? So essentially, prefix frequency of I will essentially be a dictionary. Dict frequency count of each letter in So essentially, prefix frequency of index I will essentially be a dictionary where the keys will be the letters of the English alphabet, and the values will essentially be the frequency of that key, right? So for example, if I take this substring instead of S, right? So this will be prefix string of 2, right? Because 0, 1, 2 inclusive. So from 0 to 2 inclusive. Here essentially would be a dictionary where the key A points to the value 2 and the key B points to the value 1, right? Because there's 2 A's and 1 B, right? And so that's kind of the point. So essentially prefix frequency of I will essentially map to a dictionary with all the keys being the English alphabet letters, of which there's at most 26, so constant many, and essentially the frequency of each one, right? So how many times it appears, right? And so that way we can leverage that later on, so that essentially whenever we have the leftmost and rightmost index of any letter in the alphabet, we can then say, hey, okay, we'll get that index, we'll do +1 and then the rightmost index -1, right? So for example, from these B's that I was showing before, right? We don't want to include the left and rightmost B's together, right? We only want to consider the palindromic substring BBB, and there's at least one more B sandwiched in between those two, so that's why we do +1 and -1 here. But essentially, what we can do is like, okay, let's grab that dictionary of like, essentially, here I should really call this DLDR, right? DR. It's just that I had it as another function beforehand and so on, so that's why I had it that way. So yeah, I'll just submit it with DLDR. There we go. So essentially, now I should what I'll have is essentially, okay, I want the frequency count of every single English letter between index L and index R, right? So what I can do is apply the prefix sums idea, like I've been doing in the past 2 videos, where it's like essentially it's like, okay, what I want is like the subarray sum of any subarray from any index I to J, or in this case L to R. Here we essentially apply that exact same idea, where it's like, okay, we're interested in the frequency count from L to R. Great. We're gonna say we know that prefix frequency of R is essentially the frequency count of every letter from index 0 to R. And if we take prefix frequency of up to L -1, here's essentially what happens, right? Prefix frequency of R is essentially equal to prefix frequency of is essentially equal to a frequency count of, let's just call it like this, let's just wrap it around like the frequency dictionary, but essentially it represents from 0 up to R, right? That's the point, right? The frequency dictionary of the letters from 0 to R instead of S, right? Which is essentially the same thing as taking this from going up the way up to L minus 1 inclusive, right? Plus the same thing, but then going from L minus 1 plus 1, so the next index, all the way up to R, right? So if we go 0, like, right, this should be true, right? If I do I, right? For any index I that is like, you know, between 0 and R, this should be totally valid, right? So essentially it's like, you know, the count from, you know, of the frequency of each letter from 0 to I, plus, you know, the count of all the frequencies of each letter from I plus 1 to R will essentially be the same thing as going from 0 to R, right? It's just like, you know, I don't know what it's called, like, you know, addition is cumulative or associative or whatever it is, whatever the proper mathematical term is here. And like, it doesn't matter what index I split things off, right? Like, you know, it doesn't matter the order in which I do addition or if I split things, right? 3 plus 4 plus 5 is the same thing as 5 plus 3 plus 4, right? It's the same thing, right? So here, I can essentially split up, you know, the frequency of the elements from 0 to R as like, you know, the frequency of the elements from 0 to I, also concatenated with essentially with the frequencies of like, you know, each letter from I plus 1 to R, right? So it's like, yeah, it could kind of forgive me for the abuse of notation here, but the point is like, you know, if A happens 2 times in here and A happens 3 times in here, really just means that like, you know, 2 plus 3 is 5, which is essentially how many times A happened from 0 to R, right? Essentially splitting it that way, right? But once we essentially understand that, right, one index I that can essentially make it is L minus 1, right? Let's just choose the index L minus 1, right? So here I'll just do I is equal to L minus 1. And so here minus 1 plus 1 essentially becomes L, right? And essentially from this, if I subtract from what I really care about is this guy, right? We want the frequency count of every single character from L to R. But here, essentially, if I do prefix frequency of R, I have an overestimate of, you know, the frequency count from 0 to L minus 1. But remember, I always have access to the frequency count from index 0 to any other index. So here I'm overestimating from the frequency count from 0 to L minus 1. So let's grab the frequency count from 0 to L minus 1, right? Because this is the same thing as prefix frequency at index L minus 1, right? Because by definition, for example, the one for R was from 0 to R. So if I do for L minus 1, it'll be 0 to L minus 1, which is exactly what we have here. We have this plus that. This is what we're interested in. So we subtract that from a result, and there we go, right? And so here what I do is like, okay, for every single key in DR, we just want to know if, you know, dr of key minus the 1 from L is greater than 0, right? Because again, we're subtracting this guy, but here I just rearrange the formula, right? So it's like if I want this minus this greater than 0, I can just add this value on both sides, right? So if I add it here on the left side, it essentially cancel it out. Here I add it on the right side, 0 plus anything is just not anything. So that's why I essentially do it this way, right? But essentially it's like, you know, I want to essentially kind of subtract the frequencies of those two dictionaries. So it's like, you know, for every single thing inside of like, you know, my dictionary of R here, it's like, okay, for each one of these guys, right, I want to make it so that like, you know, the frequency count of that letter minus the frequency count of the letter all the way up to index L minus 1, because I don't have access to those. I want to make sure that, okay, if it's greater than 0, then fantastic, I have at least one occurrence of that letter, right? And here, like, since dictionaries are unique in terms of their keys, and like, you know, the keys represent the English the lowercase English letters, and essentially it's like, you know, we're gonna loop over all the lowercase English letters that, like, you know, happen all the way up to index R inside of S. Essentially subtract the frequency counts of like anything that happened from 0 to L minus 1. And if the count is greater than 0 at any point, and remember here we just rearranged the formula, but this is really just asking if their subtraction is greater than 0, then that means like at least one letter, at least one occurrence of that letter occurred between, you know, L and R that is of interest to us. So there exists a unique palindromic subsequence of length 3 using this letter as the middle letter, right? And so essentially we do that for every single letter inside of DR as the keys, because again, the keys are the lowercase English letters, and that way we correctly update result, right? And so I know it's kind of a lot of convoluted kind of details, but at least I hope that the general idea picture kind of makes sense, which I can just kind of reiterate one time quickly here, which is essentially the idea here is go through every single letter in the English alphabet, right? A, B, C, D, E, F, G, H, all the way up to Z. And for each one, it's like, okay, I want palindromic substrings that start and end with that letter, right? So starting with the letter A, I want palindromic substrings that start with A and end with A, which means I need to have a letter in the middle. So what do? I grab the leftmost index of A, I grab the rightmost index of A, and I'm like, great, let's look at the letters in between that, right? Let's count the number of unique letters that are in between those two indices of A, and that's essentially the unique palindromes that I can make, right? If the unique letters between the leftmost and rightmost index of A happen to be B, C, and D, right? Then I'll have one palindrome that is ABA, one that is ACA, and one that is ADA, right? So I'll count a total of 3 palindromic substrings, right? And so that's kind of the idea. For every single letter in the alphabet, grab its leftmost index in S, grab its rightmost index in S, and count the number of unique letters between those two indices to essentially count the number of unique palindromic substrings of length 3, of subsequences, I should say, of length 3 that start and end with that letter. When you cover all 26 letters of the English alphabet, you essentially covered every single possible unique length 3 palindromic subsequence, because the letters of S are limited to lowercase English letters. So hopefully at least that general idea makes sense. If the coding explanation in terms of how I was able to do it did not make as much cohesive step-by-step sense, right? Because I know it's kind of a lot of details to just throw at you when I was the coder of the solution. And it all makes sense in my head because I'm the one that wrote it, versus trying to explain it. And I can understand, it's not as simple to understand someone else's code, right? It's a lot easier to understand code that you wrote on your own. So, so sometimes I might do a bad job explaining that, but at least, hopefully the general idea of what I implemented makes sense, so that maybe then, how I did it maybe makes a little bit more sense, right? And the point is that once you're looking at any two letters, starts and ends with that letter, and you're trying to count the number of unique letters that happen in between there, that's where I'm using this prefix sum idea, so that I essentially can do things a lot more efficiently, in constant time with the O of n, at the end of the day, it's an O of n algorithm. It's just that I happen to do one O of n parts at the beginning to essentially do the prefix sum work, and then that way, whenever I loop through all the letters of the alphabet, I essentially can do O of 1 work, right? But in here, if you really wanted to, like we did before, you can just go from this index to this index over here, keep track of a set, and just count the number of unique letters as you go, and just add that registration, right? And that means it's for every single letter in the alphabet, you'll do O of n work. But in total, by the way, sorry about that. But in total, it'll technically be O of n work, because how many letters are there in the English alphabet? 26. So 26 times O of n is still O of n. And we actually tried that solution earlier, and it actually works, right? And I can just prove it to you one more time here. It's just if I do a hash set is equal to a set here, and I just say hey, for every index, right, for every index in range from that index L all the way up to R inclusive, right, here we'll do hset.add, the letter at index here, and here we'll just do res plus or equal to the length of the hash set, right? That'll be the unique letters between L and R here, so we'll add, that count to res, and here if we run this, we'll see that it works absolutely just like a charm, right? We'll just let it run, we can submit this, and we'll say this works perfectly fine. So if the prefix sum way that I did things doesn't make sense, you can, this one should at least make sense. And technically, yeah, it's a little slower, but technically, in fact, I could even just eliminate this work over here, right? Let's see if it's even faster, actually, right? Maybe it's even faster. Not really. We get to 56%, 73% is technically a little bit better, but technically this is an O of n solution as well, right? So you could have gone this way. It's just that I chose to do the prefix sums-ish kind of route for this problem, just because it made a bit more sense to me while I was coding it up. But technically, you could do this solution as well, where it's for every single letter in the alphabet, of which there's constant many of them, you can essentially do O of n work, right? It's just that I chose to do O of n work at the beginning, but also abusing the fact that the frequency, the dictionaries here, I can do .copy because 26 is a constant number of letters in the English alphabet, so this is constant work every single time, using the same notion, right? It's would you rather do O of n work where you're cheating the constant work, or it's would you rather have an O of 1 loop where you're cheating that constant work and having O of n inside of it, right? At the end of the day, it's kind of the same thing. It's just in my mind, this is just how I thought to solve the problem, and it turns out to be a little bit more efficient, which of course, if you can pre-compute work to be able to use it over and over later on, always usually kind of a smart idea, right? But technically, if you did it the other way, where you just count the number of unique letters between any two indices and you just do O of n work for it, hey, more power to you. It's just, you can do it with prefix sums, but hey, if you just do it linear time, it's fine. There's a constant amount of letters in the alphabet, so technically your solution is O of n, so in terms of big O asymptotic complexity, you had an optimal solution. So you actually don't even need to do prefix sums at all and still arrive at a technically optimal solution in terms of big O asymptotic complexity, as long as, O of n is the optimal solution. But I'd be surprised if it was not, right? I don't think, so it's not really possible to do this in better than O of n time. You have to go through, you have to go through all the string of S, so you just at least be able to find every single possible unique palindromic. in terms of big O, right? It's like yeah, obviously if they're all lined up at the very beginning and you have the world's greediest algorithm, then it's like, okay, great, but like, you know, there's always a worst case where it's like, you know, that doesn't work, right? So yeah, I don't think you can get this better than worst case O of n. It wouldn't make sense. But yeah, but hopefully, at least the general idea behind my solution made sense. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.